Hello, everyone. I wanted to give you a tutorial on ADT, which I think should be interesting for mostly for beginners, but also I try to include stuff that's newer, has been added recently over the last year or 2 years. So I think, if you need a refresher, this may also be a talk for you. And I wanted to give you a little bit of my personal background. So I've been contributing to LVM since I think 2015. So it's been roughly 8 years. And I worked on a bunch of projects, both within LVM, within Clang, MLIR, and also on external projects that used LVM in their implementation. And as I kind of moved from place to place, company to company, what happened is that I was often asked to, do some coding interviews, like perform coding interviews, but also take the coding interviews. And one of the first questions that I often ask is like, okay, so in my solution, can I assume I have LVM libraries, or do I have to use plain C++? So when people tell me, yes, sure, go ahead, and it's fantastic, I'm at home. When people tell me, no, just stick to plain C++, no LVM, then I can do that, but it's kind of painful. It's like going back to banging rocks. So I would argue that there must be something that makes people adopt LVM for their implementation for all of these downstream projects, and also for all of the academic work. It's probably not just the pure theory behind it. It's not that they like exactly how the IR is implemented. I think it's something about the coding style that they appreciate, something about the testing style that makes it nice to work with. And I would further argue that one of the biggest components that actually makes a difference on when you do your work day to day is actually the ADT, all of the utility functions, all of the containers that are available for you to use. So I wanted to give an overview, like a guided tour of LVM's ADT. And I also wanted to give an advice for new contributors. So as I said, this is supposed to be a beginner-friendly talk, so you don't need to be an LVM expert. You don't need to be a C++ expert. This is not a CPPCon talk. And I would like to just show you what is available for you to use, explain some implicit assumptions, some unwritten rules, explain why things are the way they are, and also guide you through writing your first ADT patch, because this is something that can have a steep learning curve if you don't know how to deal with all of the compile times and having to recompile most of the projects, because almost everything includes ADT. And this is also not a definite difference. If you want to read something offline, I think there's a very good explanation that gives you overview of different data structures, different functions available throughout LLVM ADT. And this is the go-to reference. And I won't cover nearly as much content as you can find on the website. So to get started, C++ comes with a pretty good standard library. And historically, we've been talking about STL as the subset of the standard library that contains all of your containers, algorithms, iterators, and more recently, type traits and other other stuff you can use for metaprogramming and so on. So here's your typical example of C++ code. So we have some vector that can be generic over the data type. You can write your own type and use it. You can make a dynamic array out of a vector. You can sort it. Sort doesn't need to know exactly about your implementation details of your type, as long as it knows how to compare elements. And the way we kind of combine these data structures, like containers and algorithms, is that containers expose iterators that are handed to algorithms that operate on them. And this is state of the art as of C++ 17, which is the version that LVM currently uses. And ADT in LVM, it stands for abstract data types. If you grep for it, there's actually no explanation what ADT is. But I think this should be the correct interpretation. And it's an extension of like C++ STL with some nicer ergonomics, some containers and functions that are simply not present in C++. And this is probably partially because some of these are specific to LLVM, and some of these take some shortcuts that make the implementation doable. That would take a lot of time to agree on and standardize in a full standard. So here I have an example that should look familiar if you've been like an LVM or MLIR contributor. We also have our own containers, our own utility functions. It's a different flavor of writing C++. But if you move from like an LVM project to another LVM project, you should mostly feel at home. And I started talking about these like differences between STL and ADT, and because this is designed exactly for LVM and the uses within LVM, we can take some shortcuts. For example, like LVM doesn't use exceptions, so we don't have to worry about exception handling and all of the complexity that comes from having to consider what happens when something froze, when you move something, and things like that. Also, we don't have to accept custom allocator types, and we don't have to give any guarantees about being able to link like old code with like a new version of LVM. As long as the whole project compiles, you are generally free to change these APIs and iterate on them. And now I want to move to a section of this talk that tries to show you some of these nice APIs. And if any point you have a question, you can interrupt me during the talk. You don't have to wait until the end. So if something is not clear, just walk to the microphone and ask right away. So I guess the most common container that you see across all of LVM is small vector. It implements the same data structure, which is a dynamic array that handles the dynamic growth. Like you can add more elements. You don't have to specify upfront like the total number of elements that you expect. But the implementation is different than standard vector from C++. First thing that you'll notice when you look at the implementation is that we don't use pointers for size and capacity. We use integer types, size types. And there's also an extra member with a storage inside the vector object. So I have an example here of a small vector of ints. And you'll see that the size of the stack object, the vector itself, is quite large. And what happens is that we have all of the usual fields with your pointer to your data, the size, the capacity, and also then inline inside the object, we have enough storage to allocate the first 12 elements. So when we are within the for loop on the slide, we are still within the small storage, and we don't have to do any heap allocations. And after the loop, after we add the 13th element, we have to allocate a new storage, move all of the elements over there, and then we don't use this stack storage anymore, because this must be a contiguous array in memory. So it's like one chunk. And you can also manually specify the size. So you'll see that if the size is small, it can happen that the object itself is smaller than std vector. So if you want to optimize for like stack size, this is actually useful. Or if you know that the number of elements will actually be large, you can still use it. It still makes sense. For some size, for example, like on my system, for 2 elements, this takes as much space as standard vector. And as a consequence of using these integer types for size, we have to be careful about like the total number of elements that we can hold in a vector. So if we use unsigned 32-bit integer, we can generally hold something at the order of like the 2 to the 32 of elements. So there's a code path inside the definition of small vector that says, oh, if your pointers are 8 bytes large and the type is smaller than 4 bytes or something, it's actually going to use 64-bit integers so that you can have for example, a vector of characters that holds more than 4 gigabytes of memory. And this is something I believe a little bit newer. Sometimes you have code that produces some results and then you want to pack them into a vector. And the traditional way to do it would be to construct a vector and then insert elements into it. So you can, in the constructor, you can provide, this is the iterator to the beginning of the inserted elements. This is the iterator to the end. And we have a nice wrapper function that takes a range of elements and it will do this construction for you. And what's also nice about it is that we have a second helper function, toVectorOf, that also allows you to specify the type of the elements that you want at the end. So for example, if something returns you a list of integers, but you want a small vector of size t, it's possible to do this conversion in just a small, concise one-liner. In general, the technique that small vector employs is called small object optimization, and we have a number of different containers that use a similar, they employ the same technique. We have small sets, we have small maps, we have containers that are optimized for holding pointers, we have small containers optimized for holding strings, bit vectors, and the main consequence of using the small vector optimization is that not only you save on the cost of allocations, but you also gain the data locality by having everything within the stack object itself. Next, I guess the most common container that you can see used across LLVM is dense map. It's a hash map, and the difference between the hash map implementation that you find in C++ and the dense map in LLVM is that it's also optimized for data locality. So instead of holding basically a vector of linked lists with elements, it's a flat array with open addressing. And all you need to do to use dense map on most of the types, you just use it. It's already supported for most of the standard types like your ints, floats, pairs, and common LLVM types. If you have some custom type that maybe lives downstream outside of LLVM, all you need to do is specify a couple of type traits, and then you can use it. So basically, you need to tell it, how to hash how to calculate hashes, and things like this. We also have a custom type for holding references to strings. So this can be references to std string, C strings, and so on. And this predates string view from C++. It's roughly the same container. It holds the pointer to the start of your string and then the length of the string. So this is much nicer to work with than using strings that you have to copy and allocate every time you copy, or having just plain pointers to char that force you to recalculate the length of the string by looking for the null character at the end. We also have a type called string literal, which allows you to construct basically string refs over constant strings. So they can calculate the length of the string literal at compile time. We have similar things for arrays. We have arrayref, which is for immutable references to some array. It's like a view over array. And we have a mutable version. C++ added something similar recently called span. So you have a span of const or non-const elements. And this is roughly the same data structure. It's just our implementations earlier predates span. So this was just like a very quick tour of, I think, containers that appear the most in your typical LVM source code. And now I would like to talk about some utility functions. And I think one thing that you'll notice is that in C++ 17, you have APIs that are defined over iterators to containers, and LVM typically prefers to have to use references that are that require a single parameter to express what is the content that you want to modify or iterate over, and so on. And most of these functions are kind of specific to LVM. So we have a number of wrapper functions that take the existing algorithms from C++ and just package them in a way that's more ergonomic to use. So for example, we have LVM sort that takes a range instead of a pair of iterators. And the benefit is that this is less typing. So less typing is typically better. And not only that, you cannot get confused and, for example, pass in iterators from like two different objects and end up in some runtime errors that are difficult to debug. And it also allows us to introduce our own custom checks like on top of these standard algorithms. So for example, for LVM sort, if you enable expensive checks, which is like a CMake define, you can specify at build time. We can first shuffle the data before doing the sorting so that we can exercise different orders because the sorting is not guaranteed to be stable. We also have a number of common range functions. So for example, we have reverse for getting a range that can be iterated over backwards. And then we have like two of my favorite functions, isContained and allEqual. So I think these are fairly self-explanatory, but because this is something that's completely unique to LVM, we can make our own design decisions, and this is not it's not just like a simple wrapper over an existing function in C++. So one code pattern that I see appear very often, especially when working with enums that describe some targets, some like registers, or like whatever categories of things that you may be concerned about, you'll end up with a lot of comparisons that check, is this like one of these possible enum values? Or you'll have, is it that all of these values, all of these variables have the same value? And what we exposed in LVM is a version of this function that takes an initializer list, and you can hand it a number of elements to check. So for example, if you want to check if k is one of these enum values, you can just put them together in an initializer list and check without kind of repeating the same comparison over and over again. And with 3 elements, it's already nice, but if you have larger sets, this really makes the code much more concise. We also have a nice utility function for appending multiple elements to containers. And this is I found it very useful when specifying different capabilities that are supported by different target devices. And this allows us to just have a range of supported capabilities that we put in an array, and later we can append all of them at once to the vector. And this can be generic over the container type, so that it doesn't work only with small vector, but it can append to other containers as well. One of my other favorite functions is enumerate. And this is super useful when you want to iterate over something, and at the same time you want to know the index of the element that you are iterating over. This is like very common also in Python code. So if you write Python, this should be familiar to you. The way it works is that we move the input range. So for example, here arg names inside the enumerate, and later have a second range of all of the indices. So what is being returned is a 2-element tuple with references to the elements that we're iterating over. One will be just size t for the index, and second one will be the reference to the current element of the input range. And this actually generalizes to more than one input range at a time. So it's possible that you have something like I don't know, for example, like a function signature that has a number of function types, and also each of these arguments has its own name, and you can iterate over like all of them at once and keeping track of the index. And one thing that I want to highlight is that because the way it works is that we create this new range that is being returned from enumerate, and after that we just keep incrementing all of the iterators to each of the iteratives. We get a tuple of references to the elements. So it doesn't, if you put const or like constraint ref in front of the all of your loop variables, it doesn't actually make the references const. It makes the it makes the tuple itself const, but the references within the tuple are non-const. So there's 0 point writing something like const autoref and then all of your variables. And this way is also shorter. We also have a number of zip functions that are super useful when you want to iterate over multiple things, but you don't care about the index. These have the same semantics as enumerate, in a sense that zip, they move all of the input ranges so that you don't have to worry about temporaries. And zip equal specifically has also an additional check that makes sure that the number of elements of the input ranges is the same. So for example, if your arg names array has 3 elements, but alternative names has 4 elements, in debug mode, it will just assert and complain that the ranges you are iterating over don't have equal lengths. And in release mode, this assert disappears, so we get good performance. And further than that, we don't even have to check if we've reached the end of every single range that we iterate over. We only have to check if we reach the end of the first range, because now we can assume that all of these have equal length. We also have a number of alternative zip functions that support different scenarios when this behavior that I described is not desired. So for example, with zip, the iteration will stop when the end of any of the ranges is reached. So basically we'll stop as soon as any of the ranges stops. We have zip first, which is similar to zip equal, except it assumes that it's always the first range that is the shortest. And we have a counterpart called zip longest, which continues to iterate until the end of the longest range is reached. And when there is no element, because we exhausted all of the possible elements of the range, it'll just return a null opt. We also have a couple of helpers for dealing with sequences. And here specifically, we have sequences of integers and sequences of enum values. This is useful for kind of, because we have a number of nice algorithms that operate on ranges in LLVM. It's useful that you can have a function that actually creates a range that later you can manipulate, you can filter, you can transform, you can map over. And we have this utility function called seq, that stands for sequence, that allows you to create these ranges that you can later manipulate. There are a few variants, and this is, I would say that the closest counterpart that comes to my mind is like the range function from Python. So you can request, just elements from 0 up to n, but not including n. You can there's an overload that takes 2 arguments that is the start of the range and the the end element, and then you can also have a request the range to be the sequence to be inclusive, so to include the last element. What I found often when writing, when dealing with a lot of code that deals with like externally specified enums, is that people write code that assumes that enums have that will basically try to iterate over all possible enum values, and they assume that the enum values have consecutive values. And in general, this is not safe, and this is kind of awkward when you write it by hand. So if you are using just pure C++, you would write the for loop that starts at, you have to cast your enum value to an integer. Later, you would have to increment the integer, and every time you use it, you have to cast it back to the enum type. And this is sort of annoying, and it's also error prone, because at every place where you want to iterate over enums, you would assume that the range of enum values is contiguous. And this may not be the case. It may be that, you changed your enum definition, you added some values, now you have holes, and now it's very difficult to grab for all of the for loops that try to iterate over it. Like, this is just like too many ways to write this for loop manually. So what I found is that it's useful to have a way to specify that this enum is iteratable, and as long as you specify this trait, this can be just after the enum definition itself. This enables iteration with enum over such enums. So this is something that I think both makes the code much nicer, because you don't have to deal with all of the casting between enum types and integer types, and also allows you to have just like one place that declares that this enum type is actually safe for iteration. This is something that I would like to skip over, but you'll see this a lot in LLVM. We have a lot of functions that allow you to iterate over graphs. And the principle is similar. You have functions for iterating over graphs, and to support your custom graphs, you just have to provide your graph traits that specify, how to get all of the children of your node, and so on. So this is tremendously useful. And the implementation of some of these are highly optimized. So if you ever feel like, I need to write my custom topological sort, I need to write my custom DFS, BFS, I would recommend you to check if you can use some of these graph functions first, like the first, post order, SCC iterator. And there's also a trick that if you want to customize exactly the elements of the graph that you visit, you can actually provide your custom storage that decides whether elements are visited or not. So it's possible that you already pre-populate this storage with elements that should be considered visited and won't be visited again. Here are a couple of other things in ADT that I consider super useful. We have a custom type that combines a pointer and an integer. So for example, like if you know that your type has some alignment, you should be able to use the bottom n bits. And if you're on some other operating system, you know that your 64-bit pointers actually only have like 48 bits that are used for addressing. So it allows you to have like a compressed representation of a pointer and a small int. Another of my favorites, especially for dealing with legacy code, is scope exit. And this is scope exit is a utility function that takes a functor. So this can be something like a function name. It can be something like your lambda, and it will call this function at the end of the scope. So you can use it to deal with functions that assume some handles, like something like fopen, malloc, that you want to be like closed or deallocated at the end of the scope. So I would say that this concludes a tour of my favorite parts of ADT. And now I would like to move over to a section of the talk that talks about, how can I contribute? And I found that, at least for me, this was initially very painful, because very often you look at the header, you want to fix a simple typo, you want to test your code again, and then you realize, okay, I have to recompile absolutely everything. And this initially would make me say, okay, like I don't care about this typo that much. I'm just gonna forget about it. I'm not gonna wait for the whole project to recompile. And there are some ways to deal with that. And what I recommend is that basically you need to reduce the scope. You can, start prototyping your new addition. You can start prototyping your new ADT function in isolation in a unit test. And after that, you can move it to one of the main headers that you care about. And then you can, you can try recompiling only actually the test target that you need. And once that test target works, you can move forward and see, okay, can I compile all of the unit tests? Once all of the unit tests compile, you can see, okay, can I compile like all of LVM, all of Clang, all of MLIR? And this makes it much more sustainable. Like it reduces compilation times from like minutes to seconds if you want to just iterate on something quickly. I would also like to recommend trying some other linkers if you use your like default system linker. Like linkers like Mold or LLD are amazing. Like they improve compilation times so much. And one of the differences between like your typical ADT code and typical like LVM compiler code is that LVM uses textual representation for testing with lit and file check. So we will typically, try to compile something, dump some output, see if the textual is the output as we expect. But this is not really suitable to exhaustively testing if your standard library implementation is correct. So most of the ADT tests are written in Google Test, where you can you just write C++. You can make sure that you actually exhaust all of the possibilities that you care about. I think there's also another like way of writing tests that is underutilized, especially when dealing with containers and sequences. Gtest comes with gmog, and they provide some abstractions over checking if your container or your range has all of the elements that you expect. And you can specify that you want all of the elements to be there. You can have that, you can check that unordered elements are exactly like you expect. So you want to find all of them, but you don't care about the order. And this makes writing tests over ranges much simpler and much more concise. And actually, if you have a test that's failing, it also makes it much easier to see where the failure is, because they have some nice printers for telling you, what was the expectation and what it actually found. So compared to like a sequence of checks that, element at index X is Y, I think this produces like a much nicer debugging experience. For all of the APIs that have some contract around assertions, we should actually test the assertion code, because if it's not tested, I assume it doesn't work. And we have a mechanism for testing if assertions were actually triggered or not. So these are called dev tests, and we can conditionally execute them. So if dev tests are supported at all, and if we are in the debug mode, then we can check that the assertion is, that assertion fails, and we can further check that the assertion message is what we expect. I have like a bit of a warning that if you use this excessively, this can be really slow, because it causes your process to be forked. So if you are using dynamically linked libraries, you can keep forking and loading the same dynamic libraries over and over again. So like the recommendation is that this is fantastic for testing, but please don't put dev tests inside loops that iterate over some like combination of conditions that can fail. Like a handful is enough. And like last, kind of like a personal warning, try not to land everything on Friday evening, because ADT code is very good at exercising compiler bugs in all of the build bots. And they will fail, and they will take a few hours to propagate the failure back to your email. And you don't want to wake up, early, in the morning and figure out, okay, how do I get this version of Visual Studio on my machine to fix that. Yeah, like submitting during the weekdays is a much better experience, at least for me. Yeah, so in summary, I would like to highlight a few things that I would like folks to take away from this talk. Is that we really have a nice set of containers and algorithms in LLVM that make life simpler. These provide like a very performant implementations of a lot of algorithms, data structures that is like robust, well tested. So there's like little reason not to use it. And these come with nice ergonomics because they're mostly designed around ranges instead of iterators. It's good to consider, what is your contract when it comes to assertions when you design these functions, and make the expectations clear, especially when you write the documentation comment. There are a lot of ways to kind of teach this code about your own types, and this is primarily implemented through type traits that you have to specify for your own types, even if it's downstream. And if you want to contribute, make sure you don't try to compile everything at once after you make a simple change to one of these headers. And this is all I prepared for today. And now, if you have any questions.
If you have any questions, come on up to the mic.
Koja?
Hey, yeah, fantastic talk, Jacob. So I had a question about the ranges. I was curious what the ownership of that is, such that like you showed examples where you have a sequence that creates a range, and then you can manipulate that range, like reverse it, take a subsection of it. So
like this one?
Right. So, if you take the sequence and then you return toString, where's the data stored? Like how if it goes out of scope, will it be
No. So C++ has a rule that the lifetime of these kind of temporaries is extended out until the end of the expression. So in this case, all of the kind of intermediate temporaries will be, will stay live until the end of the return.
I see.
So this will be taken care of. But I had another example where we had a for loop that had like enumerate or zip. And in C++ 17, there's no rule to say that the lifetime of these temporaries is extended until the end of the loop.
Right.
So what we had to do is we had to make sure that we actually move all of these temporaries into the enumerator object to make sure that they don't die while you are iterating.
Right. And if this sequence was manipulated and then returned to column function, would it still be live?
So in this specific case,
mm-hmm.
It's fine because you have a temporary, you use it to come up with a new vector, and what you return is a vector of new elements. So you don't really care about this sequence. This sequence it's already out of scope. You don't need it. There's no reference to the sequence anymore.
Right. I guess maybe not this specific example, but in general, do I need to think about if I'm passing ranges around their lifetimes, especially if they're going through functions?
I would say you may need to think about it if you are using something like arrayref or stringref to make sure that the references that you hold to these objects, actually point to valid live objects. Yeah. But when it comes to just composing ranges and doing some transformations, I think in general it just works.
Awesome. Thanks.
Hi, thanks for the talk. I have a question about the seq enum. It looks like magic. What does it know about enum? Does it know the last element, or does it know holes?
No.
How does it know anything?
So there's a chance that you say, oh, your trace specifies that your enum is iterable, but really it's not, right? So for example, you could have that you have element R4 with value 10, right? And then you have a gap. And there are two interpretations. Maybe it's exactly what you wanted. Maybe you actually wanted to have values that don't really have any kind of enum name, but appear in the range, and this may be fine. And maybe that is a bug, right? So I would say that it depends on the case. And I had another version of this implementation that had more safety checks. So initially, when I contributed this to LLVM, I had a version that also forced you to specify the first element that's iterable and the last element that's iterable, or like the end element. But at the end, I think that because most of these traits definition will be just after the definition of the enum, I think it's rare enough to make this kind of mistake that it didn't justify the extra cost of specifying this.
Okay. So basically, trust you in.
Yeah, but
like if you say it's iterable and you have holes, then it's your problem.
Yes, but it's like a single point that you have to make sure that it's correct, right? It's not like you have to go over every single for loop and check. It's like you specify it in one place, and if you have a bug, you have it in one place only.
I see. Okay. And you need to remember, like, constantly correct the end one, the last one. If you add a new one, like either for, I need to update.
Yeah, but now you have a function call that you can grab for. You can just grab for enum_sec.
Yeah, I guess so. Yeah, sure. Thank you.
Yeah, I had a question. You explained that some of these ADT things predate the same concept being standardized in C++. Sometimes I noticed that the ADT thing gets replaced by the standard. I think there was an LLVM optional that got replaced by STD optional. Are there any plans to do that with the other things that you mentioned, and maybe even do it with the ranges at some point?
Yeah, I think that's true. That's the general trend that we have. That if there's an equivalent in the standard that's like good enough, we try to like gradually align the APIs so that at some point we can just switch over. And usually this is a process that works on like a case-by-case basis. And I think we'll have like a big question that we'll have to kind of answer, like have a discussion on Discourse. What do we do when we eventually adopt C++20 and all of the range APIs that come with it? And I don't know what we will decide as a community.
Okay, thank you.
So follow-on question. When we do move to C++20, there'll be some semantic differences to what we have implemented here. Because C++20 is always lazily evaluated. Some of these, for example, take, it is not lazily evaluated because it has compute the end of the range that it's going to take. So how would we deal with that?
I would need to look at the spec. I haven't thought about it.
Okay. If there's no more questions, we can thank the speaker.